This worksheet is intended to give you some more examples of problems like the exercises that are in the book for section 1.2. In the first problem, we have a couple of descriptions of sequences, and we're trying to find a recursive or closed formula for them. So the main thing is to first identify the pattern, and you can see in the first example that the pattern is that you're multiplying by 3 each time. And in the second problem, it says the sequence starts with 10, and each entry is 6 more than the previous entry. So the pattern, if you had to describe it, is that you're adding 6 each time. So, so if we're trying to write this as a recursive description, we would say that each term is 3 times the previous term. So that's supposed to be an A. So AN is equal to 3 times AN minus 1. Again, the N minus 1 is all in the subscript. And let's say A1 equals 2. Sorry, my writing's not caught up with me this morning yet. And A1 equals 2. So this is our recursive description. To find the closed formula description, we want to compare this sequence to a sequence whose formula we know. And so the other sequence that has a times 3 growth pattern that we know the formula for is the sequence that has the formula 3 to the n, just the powers of 3. These will look like 3, 9 is 3 squared, 27 is 3 cubed, 81, and so forth. So if I compare, let me get rid of this. So if I compare these term by term, it may not be too obvious at first, but remember when we did one of these before in class, the relationship that we saw was not additive, it was multiplicative. So I don't want to see that the bottom numbers here, that these numbers down here are just 1 more, 6 more, 9 more, whatever. I don't want to look at the difference, I want to look at the ratios. And if I looking for ratios, I see that the numbers on the bottom are just 1.5 of the numbers on top. So 1.5 times 2 is 3, 1.5 times 6 is 9, 1.5 times 18 is 27. In other words, these terms occur in constant ratio with each other. And so that means that if the bottom row has formula 3 to the n, then the top row will have formula 2/3 of that. And that can be simplified. We do have a power of 3, and we can compare that to the 3 down here. So if you wanted to combine that, you could to simplify it. But this is perfectly good as a closed formula, and you'll see that it works. And this is good as a recursive formula. The ones where we're adding a constant amount each time, those are much easier. We always kind of hope for those. So in terms of the recurrence, I want to say each term is the previous term plus 6, starting with 10. So that's my recursive formula. And then to find the closed formula, I could start off with my AN sequence, which is 10, 16, 22, and so on. That's what's being described there. And compare that to a BN sequence that has formula 6n, just the multiples of 6. So 6, 12, 18, and so on. Because the multiples of 6 have the same excuse me, the same growth rate, but they have a nice formula. So if we compare these term for term like we did before, we see that the numbers on top are just 4 more than the numbers on the bottom, and so that means that a formula here would just be the formula for the bottom row, 6n plus 4 each time. So add 4 to your formula for the bottom, and you get the formula for the top. Okay, the next problems are the type that we did that were involved algebra. We were supposed to simplify an expression, and so this is going to get at any kind of algebra that we may need to do in this course. So AM minus 2AM minus 1, I can write algebraically because I have an algebraic formula for AN. So A sub M, this first part, that just means take your formula and change the n to m. Right? Put the m in place of n in that formula. If we do that, we get 2 to the m minus 1. Then minus 2, this is following the rest of this formula, 2 times, now I need to know what a sub m minus 1 is. Well, that just means put m minus 1 in place of n in the formula. So I'll have 2 to the m minus 1 power minus 1. So here I have the, the formula for AM. Here I have the formula for AM minus 1, and the problem is telling me to form this expression. Take the AM, subtract twice the AM minus 1. If I do that, there's not a whole lot of algebra to do here. I do have to distribute this multiplication through the parentheses, and if I do that, I'll include that extra step here. I'll have 2 times 2 to the n minus 1 minus 2. So this 2, this 2 times, the 2's get multiplied by the 2n minus 1, and then the 2 gets multiplied by the negative 1. So I have the 2 times the 2n minus 1 and the 2 times the negative 1. My rules of exponents tell me that if I'm multiplying 2 powers of 2, right, this 2 is really just 2 to the first power, then I add the exponents, and so this ends up being 2 to the m, what did I say, minus 2? I distributed wrong, right? You got to pay more attention than I was. This, we have minus 2 times minus 1, so that should be plus 2. I almost got away with it. I'll have 2 to the m minus 1 minus 2 to the m plus 2. So by resolving these powers into this expression, it looks like that, and of course these then subtract away, and I have minus 1 plus 2 equals positive 1. So this expression simplifies a lot to just be 1, regardless of what m is. In the second problem, it's a similar idea, but it's a little bit different because the algebra is different. We don't have to use rules of exponents because there really are no exponential expressions here. I do have to find a sub m, so that's m squared, and then I have to find a sub m minus 1, which is m minus 1 squared. So I have to make sure that when I'm putting m minus 1 in for n, that I put the parentheses around the m minus 1, so that remember that I'm squaring the whole thing. Putting the m in place of n is, of course, easier. So this I should use FOIL, and I'll do that without taking the parentheses off first. M minus 1 squared is n squared minus 2m plus 1. Right? It's really m minus 1 times m minus 1 using FOIL. And then when I do this subtraction through the parentheses, the m squareds are going to actually go away. I'll have m squared minus m squared. And what I'm left with is positive 2m minus 1. For the next problem, again, it's just describing a sequence. The easiest thing to do here is just write down a few terms of the sequence and then treat it like all the other problems. The nth even 2-digit number, well, these are 2-digit numbers. These are even 2-digit numbers. So that's the first even 2-digit number. That's the second one. That's the third one. That's the fourth one. So if that's the sequence I'm trying to find a formula for, then my algebraic expression is going to be a sub n equals 2n plus 8, and we do it just like we did all the other problems. I won't go through the steps. But if you if you just write down a few terms of what's being described there, then you can just treat the problem like the other ones. So the problem here is it's given to you differently, not that you have to do something different with it. And then finally with the sums, these are fairly straightforward. When we have a sigma, the indices here, the k equals 1 to 6, that means that I want to think about all values of k starting at 1 and going up to 6. So I think of all the values of k from 1 to 6. That's k goes 1, 2, 3, 4, 5, 6. For each one of those, I'm going to apply this formula. So 3k minus 1 is 2 when k is 1. Right, so I'm putting 1 in for k, and I get 2. Put 2 in for k into the formula, and you get 5. Put 3 in, you get 8. 4 in, you get 11. Put 5 in. 5 in, you get 3 times 5 minus 1 is 14. And you put 6 in, you get 17. So if I put these values of k, one at a time, into this formula, I get these values. And then the sigma here, the sigma stands for sum. So SUM, sum. So I add these numbers together. And I believe that ends up being 57, if you add them right. Changing a sum into sigma notation is a little bit harder, because to do that I need to have an algebra formula for the terms being summed. So I can pretend like this is just a regular problem about finding a formula, find an algebra formula. Here's a sequence of numbers, right? And I want to find an algebra formula for this. If we use the methods that we talked about, my formula for these terms, these differ by 4, so I would be comparing it to multiples of 4. So if I do that term for term, I find that all of these guys are just one more than a multiple of 4. And again, I'm not going to go through it again, but it's the same process we used for the problem at the top and the problems we did in class. So this is a formula that describes these terms, and so therefore this sum is going to be, I can even use the letter n if I want to. I can say n should go from 1 to 5, 5 because there's 1, 2, 3, 4, 5 terms, and then just use this formula that I found that describes the terms. And if you understand how to do number 4, it's really easy to check number 5 because you can just evaluate this sum and see if it really does do what it's supposed to do. But that should work.